Good afternoon, everyone. We'll be starting class in 1 to 2 minutes' time. Alright, good afternoon, everyone. And our first lecture for today is that we're going to be wrapping up our space and time complexity topic that we were talking about last week. And in this particular lecture, the first question is going to be the interactive question, but the rest of the questions and examples there are going to be explanatory questions where I'm going to explain to you guys why and how we approach towards getting the final answer, as well as all the explanations regarding these approaches for it to make sense, and how you would go about answering these questions if you were in an interview or for any assessments that you'll be doing this course in particular. The second lecture is going to be on arrays and strings, but we already covered that in our first year programming course. So we're not going to really be going back into this into so much detail. Instead, we're going to be looking at the application of how these arrays and strings can be used in higher order data structures. And an example of one of this will be something that we refer to as a map. We'll briefly discuss about that when we hit the second lecture in particular. But for now, let's start with our first lecture for today. And let's complete this. So for our sixth example here, we have our example code on screen. Oops, sorry. And just like last week's tutorial on Wednesday, we're going to try and figure out what's going to be the complexity for this. So I'm going to set up a poll here. I'm going to give you guys some examples here. See what is the complexity of 6. Alright, my poll should be up in a little bit. If somebody's saying they hear me very soft, is that a problem overall for anybody else? Alright, it doesn't seem like we have any general audio issues. Maybe it's something on your side. Maybe check your sound settings, if anything. See if something's getting attenuated. Alright, so I'm gonna give you guys about 2 to 3 minutes to figure out what's going to be the time complexity for this particular example. And then I'm going to give you guys the explanation as to why it's going to be that particular time complexity. And 30 seconds again for you guys to get your votes in. Alright, closing off the poll now. Let's see what the results look like once they come up in the chat. Alright, so the majority of people voted for O of n, but we still had like about 39% of the class thinking there's going to be O of n squared, O of log n, or O of 1. So the majority here was the correct answer, which is O of n, but we're going to have to focus on the explanation as to why it was O of n here in particular. Get this up here, right? So this runs in O of n time. And let's see why does it run in O of n time, right? So we start at 0 here, and then we go up to the array length divided by 2. So that means we only go up to half of that of the array length. And we iterate through each one by 1 each time. So we'll be going 0, 1, 2, all the way up to array length divided by 2. So because we're going from 0 up to half of the array length, that means that we're only going through half of the items in the array. And this doesn't really impact the big O time as such as if we are going from 0 to the full length of the array. So because we go in this sequential manner, that's why we get just O of n time regardless. The instructions in the loop here, this here will just execute once, that once. So it's really just watching how the loop here changes for us to determine our time complexity. And so long as the changing condition here is just going to be I++, this here being our uppermost limit for the for loop, so long as that isn't 1 or some other weird value, we just basically say that, okay, it's going to be a function of array length, and the array length can take any value. So if we say array length being any value can map to n, that means when we divide this by 2, it's going to be n divided by 2. And we don't really care about this divided by 2 here. We only care about what's going to be the nature of the scalability of this. So that's why we say it's going to be O of n time here accordingly. Any particular questions regarding this? Alright, doesn't seem like we have any questions. It's basically straightforward like our previous examples. All we're just watching is how the loop changes and what's going to be our start and end conditions for a loop to determine what's going to be the order of a loop in particular. Alright, so let's go on to example 7. Now from this point on, these explanations here will be explanatory, and it's not going to be interactive because I'm going to have to explain these things for you guys in order to figure out how you go about answering the questions later on when you are going to get assessed with them. So for our first question here, we need to figure out, for this entire example here, we need to figure out what's going to be the order of each of these and see if they're going to be equivalent to O of n. The quiz is going to be this Wednesday, so you're going to get a forum post after this class indicating what's going to go up on this Wednesday in particular. Originally, it was scheduled for next week Wednesday, but when we watched your timing, you wouldn't get enough time for the quiz and the group assignment in particular. So we got a lot of assignments and quizzes coming too close to each other. So in order to space it out properly and to give you guys enough time to get other things done, we're holding the quiz on this Wednesday, and I believe your first group assignment is coming out on Wednesday as well. So you guys will get a forum post indicating all this necessary information after today's lecture. Alright, so in answering this particular example here, we're going to have to figure out what's going to be the order of each one of these here, and then see if it's going to be equivalent to O of n as a result. So for our first one here, we know that p here is n divided by 2. So this comes O n plus, so less than n divided by 2. So this can be O n by n divided by 2 if we take the uppermost limit of p, because we have some mapping in between p and n. And because of this relationship here, you will get such that we drop the non-dominant term. So this non-dominant term here will get dropped, and this would just become O of n. Yeah, you'll get all those details after class when I put it up on the forum. So regarding the details of your quiz and your details of your group assignment. So don't worry. Anything else you have to ask, you can just reply on the forum and I'll respond to you guys immediately. So for our second one here, this is O2 of n, and we just also watch this accordingly, meaning that that 2 there is just, we drop those constants because we don't need those constants. We just care about if it's going to be linear in nature. So this here is also O of n. This term for O n plus log of n, we need to see which one is going to be the bigger term here in terms of if we actually graphed O of n and O of log of n. Now if we graph the two, basically we see that O of n is going to be higher than that of O log of n. What did I do here? Oops. Right, here we go. Right. So O of n here is going to be greater than O log of n. And as such, we drop the non-dominant term. So this here will just be O of n. But this final one here, which is O of n plus m, there's no established relationship between n and m. So no relationship between n and m. So this just remains O of n plus m. If there was some established relationship between n and m, like we saw in the first problem here, which was O of n plus p, we could establish some sort of relationship and reduce it accordingly. Give me 1 second. Right, here we go. Yeah. So where we had n plus p on top here, and we know that p was less than n divided by 2, we had some established relationship between n and p. So this was able for us to reduce this by using the utmost limit of p here, mapping it back to n, and we could just be like, okay, because n here is greater than n divided by 2, this will always be order of n accordingly. Same things when we're doing it for the second one, we just drop the constant term in front because we just care if it's going to be O of n in nature. The third one here was that we need to figure out what's going to be the order of n and then the order of log of n and see which one is greater. In this particular case, O of n was greater than O log of n, so O of n here takes precedence over O log of n. And for the last one here, because there's no relationship between n and m, we can't reduce this any further. We have to leave it as O of n plus m of course. Alright, any particular questions for example 7? You can write it out in words, that's not a problem. So long as you show your reasoning as to how you got towards your answer, that's perfectly fine. If it's like a multiple choice question, obviously I don't expect you guys to just have any space to write an answer, just choose the right answer. But for anything that's structured, you basically just have to write out your reasoning and so forth. How I have it drawn is basically like a very shorthand way of going about doing it. So unless it's like very clear and to the point, it's highly suggested that you write it out in words. Like the same way how I'm physically speaking as to what are the reasons going to be. It's really highly suggested that you actually put it down in words when you're writing your responses for the quiz, for any sort of structured questions you may encounter. Alright, let's go on to our next example here. Alright, so this example is more like a sort of interview type question that you would get if you were in a physical interview, where they would ask you about a hypothetical situation, and it's up to you to figure out how to go about deriving the complexity for such a hypothetical situation. So for our situation, we're going to be starting with an array of strings, and then each string here, the contents of it needs to be sorted, and then the entire array itself needs to be sorted. So I'm just going to draw like a really rough sketch here to give you an idea of what I'm talking about. So we have an array of strings here, so we can say S1, S2, S3, and so forth. And then like we can say S1 has A, B, C, S2 has D, E, F, G, S3 here can have like A, C, D, E, and so forth, right? So this here is our array. But then we have each string here having its own contents. So when we say sorted each string here, that means that we're going to be sorting each one of these strings here in such that it's going to be in some particular order, be that it needs to be from highest to lowest character, or lowest to highest character, or some other sort of order that's defined. And then after these strings here are sorted, then we go about sorting the entire array It'd be like, okay, the array needs to be like, okay, do we go from the lowest order string to the highest order string? Is it sorted in regards to length? Is it sorted to regards of the starting character and so forth? So those sort of questions are what you may have to ask in such of a hypothetical situation. So in this particular case, we're given reasoning to actually help us out, where that for sorting each string here, where we sort the characters in the string, the order is going to be order of n log n. And then for each string, where we sort all the strings afterwards, it's going to be order of n by n log of n, meaning that for one string, it's going to be order of n log of n. For all the strings there, it's going to be order of n by n log of n. And then to sort the entire array, it's going to be O n log of n. So yeah, this is a little bit complicated, but once you break it down to solve problems or steps by steps, you get the orders for each one of those solved problems individually. Now, you may think when we put them all together, we get order of n squared log of n, which is for each string here, plus n log of n, which is where we sort the array. So this is for each string where we sort all the strings with respect to their characters. So this is order of n squared log of n here. Just draw this linkage. And then sorting the array here is this part. And we say, okay, because these steps occur one after the other, we add the two. And if we drop the non-dominant term, being this n log of n here, we just remain with the order of n squared log of n, right? Now, you may think, okay, that's nice, that's how we approach our answer here regarding this, right? And that result actually is completely wrong. So the reason why this result is wrong is that n here is used in two different ways. And I physically drew this out to see for you guys to have an idea of why this is going to be different. We don't know what these lengths of the strings are. We don't know how many characters they have in particular. So these strings can have variable lengths, meaning they can have 1 character, 2 characters, 3 characters, and so forth, and they don't need to be equal in length. Each one can have how many characters no matter what. So we don't know what's the length of the string. And for any string, we don't know what that length is going to be. And then we also don't know what's going to be the length of the array. There's no relationship between the length of the string and the length of the array here. So this brings us to our first commonly encountered error when we're deriving complexities for any hypothetical situations, is that we only use a single variable n here once we have no ambiguity, meaning that we don't have any multiple variables that we need to consider. So in this sense, for us to go about doing the correct answer, we have to make sure that we resolve this ambiguity and then recalculate our complexity here. So that's why we're going to be defining some new terms here regarding how we go about calculating this complexity. So if we say S here is going to be the length of the longest string, and we don't know which string that is going to be, and we say A here is going to be the length of the array, instead of having our complexity in terms of n, we now have our complexity in terms of S and A, because there's no relationship between the length of the string and the length of the array. And then if we go back into how we reasoned it out before and we put in S and A accordingly where it needs to be, we then get our correct complexity here. So each string, instead of being O n log of n, meaning one string here, it's going to be O s log of s. And this needs to be done for every string, and when it's every string here, so I'm just going to annotate here a little bit. So this is for one string. So for every string, that's going to be the length of the array here. And the length of the array here was given as A. So that means we were doing O by A by S log of S. That's for every string. And then if we sort all the strings, we also saw that was previously O n log of n, but now it's in terms of A. So this is going to be O A log of A here. The other thing that we did not consider was that the strings needed to be compared to figure out, okay, which one goes higher, which one goes lower, and so forth. So that each comparison here will be taken O of S time. Now, the reason why we put this for S here is that we say in our reasoning, we're going to be going from the shortest string to the longest string in regards to our sorting of the array. So array sorts shortest to longest string. So if each string comparison here is going to take OS time, and we know that in sorting all of the strings, that's going to be OA log of A, that's a comparison that's going to be. So we just multiply the two together to get OA by S log of A here. So this and this here multiplies. And then we just add the two results together. And as a result, we'll get O of A multiplied by S. And in brackets here, we have log A plus log of S. Now let's watch this back to see how did we get this, right? So we had, for our first two steps here, we went up to O of A by S log of S. Let's write this out here. O of A by S log of S. And then for other steps, we had O of A by S log of A. O A by S log of A. And we need to add these two together. So we basically see that the A's here are constant. So that's perfectly fine. But we also have S log of S here and S log of A. That means we can factor that out accordingly. So that's why we get O of A here, which is basically constant regardless. And we have the S here. But then we have to make sure that we have log of S and log of A here, and the two of them are added. So that's how we get log of S plus log of A. Matching back to our answer here. And that's basically our final answer because there's no established relationship between S and A accordingly. Alright. Any particular questions regarding example 8? For effective sorting, the best way to go about doing a very effective sort is when you use a logarithmic order. There are other types of sorting that use different types of order, but because you were given the reasoning up front, that's what you end up using. If you're not given the reasoning up front, you can basically be like, okay, we assume that we are using this particular sorting algorithm that has this particular order, and then you could go about doing your reasoning using that particular order as well. But if the information is given to you, you have to use that information accordingly. You will see either if we have time, if we hit that lecture by today, if not on Wednesday, when we go into our particular sorting algorithm topic, you'll see how each sorting algorithm has its own different orders accordingly. We don't say log A of S because remember A here is going to be the array and then S is the length of the string. And that's the reason why you have to multiply the two together independently instead of them being logs. Because if I remember correctly, the addition of logs has its own formula and there's another formula for logs and so forth. So that's going to be back into logarithmic math. So it's not going to be that way you can have the two of them compiling against each other if I remember correctly. But I will double check that and give you guys a clear answer accordingly. So I'm going to write this down here so I can check that back. Check formulas and post on forum. So I'll check that back and I'll give you guys a clear answer regarding that particular question for log AS. But I believe it's something to do with the logarithmic formulas, that's why you don't do it. But like I said, I'll double check and I'll give you guys a clear answer on the forum. Alright, any further questions? Alright, doesn't look like we have any further questions. As usual, if you have any questions, feel free to interrupt. Once I finish talking about the particular point, I'll get to them. Alright, so let's go on to example 9 here. So, in this particular code that we're dealing with, we see that we have two recursive calls, which is going to be return sum node.left plus the node value plus sum node.right. And these sum function calls here are going to be recursively called here in regards to this summation function that we have here. Now, this particular function, we're going to encounter this later on when we start dealing with binary search trees. But we're going to just be analyzing this code here in terms of its recursive nature to figure out what's going to be our complexity for something like this. So we see that we have two function calls here for it to be a recursive function call, because in recursion the function calls itself until it terminates, and then we still have a node value here being added up to only. So let's analyze what's going to be the complexity of this from a recursion standpoint. So what this means here is that if we had some sort of node structure here, it's going to be similar to our recursion tree that we've been observing all the time. And then because we go node left and node right, that means for each node, there's always going to be two children nodes as of such. So because we go left and right, just to draw an illustration here, so this here could be node, and then we have another node here, so this will be node left. And then we have another node here, which is right. And then inside here will be node value. And we keep on doing that for each one of these. You may be inclined to think, okay, it follows those basically follows that basically same structure we saw for recursion tree, or we end up getting with some order 2 of n. But we're just watching this regards to the recursion. And That basically means that when we watch this regards to the recursion, it operates somewhat similar to our Fibonacci series algorithmically. So we basically have some constant time amount of work being done regarding this. So depending on the number of nodes that we have for our entire structure, mean if there's going to be n nodes, that just means the runtime is going to be O of n. So for space and time complexity, you don't necessarily need to understand what the code is actually doing in order to understand how to get to those space and time complexities of the question. All you just need to figure out is how the code operates. So we're just basically watching the logical flow of the code and just giving some logical reasons as to how you go about deriving your answers. If you're asked for, in particular, how does the code operate with respect to some sort of structure, then that's not a space or time complexity question. That's more of an intricacy question, where they actually want to know, okay, what does this code does, and how can you visually draw what it does, and so forth. But for space and time complexity, you just want to know how the code flow is, so just how the code operates accordingly. You don't need to know all the intricacies of what it's actually doing and so forth. So for our particular reasons here is that if we have n nodes, this runtime here, going left and right, means that we have an O of n for the entire thing. Because we're not revisiting nodes, we're just going to be going to each node once. Now, we saw this pattern here for recursive functions, where we had our recursion tree and our Fibonacci series and so forth. So because we have two branches at each call, that's going to be O to the 2 of some power. And we don't know what's going to be the depth of our tree, and that's what we need to figure out accordingly. So if the tree here is balanced, meaning that we have the same number of nodes on both of the left and the right, and there's going to be n nodes, the depth here is going to be roughly log of n. So that means that we go O2 to the power log of n. And if we rectify what this is going to be here, regards to our logarithmic formula, if we add 2 to some power is equal to q, and we take the log of both sides, we go log 2 of q here is equal to p, we need to figure out what's going to be 2 log of n here in some sort of fashion. So if we let p here equal to 2 log of n, and we take log on both sides, so we go log 2 of p equals to log 2 of n, and we see there that n, eventually we get p here is equal to n, so then 2 log of n here is going to be equal to n as a result. And because 2 of log of n here is equal to n, which is equal to p, that means eventually, from all this reasoning and deductions, the runtime of the code here is just going to be O of n. Which was, from our simple explanation, if we just have n nodes and we visit them once, it's just going to be O of n for our runtime. But if you're asked for the mathematical derivation and explanations, this is how you're going to go about explaining it. So you start with the recursion function, knowing that for any recursive function calls where we had 2 function calls, there's always going to be order of 2 to some power, where the power is going to be the depth of our recursive tree. But we don't know what's the depth here. So we make an assumption here that we have the same number of nodes on the left and the right of our recursion tree. And as a result, the depth is going to be roughly log of n. So we got order 2 of log of n, and then we need to figure out how to resolve 2 to the power log of n here. This is our logarithmic formula, and we just do some substitutions accordingly, and we see that basically we end up getting p is equal to n, and the entire runtime here is just going to be O of n. All right, any particular questions for example 9? Alright, so the reason why we use log here is because we say the tree is balanced, right? So let's physically draw what this tree will look like. So we know we have our start node here, and then we have a left node and a right node. Then for this here, we'll also have a left node and a right node, left node, and a right node. And we can see a pattern emerging here. 1, 2 nodes here, 4 nodes here. So then if we drew out for each one here, 1, 2, 3, 4, 5, 6, 8, right? So that's when we have a balanced tree, meaning that we have the same numbers of nodes on the left and the same number of nodes on the right. And because we see this expansion here going in powers of 2, if we need to know what's going to be the depth of our tree here, so this here is like level 0, level 1, level 2, level 3. So L0, L1, L2, L3. If we need to figure out what that's going to be here, this comes like if we take, okay, if we want to get 3 here, that's log 2 of the number of nodes plus some value. And n here at 3 is 8. So log 2 of n, meaning log 2 of 8, will just give us 3 accordingly. The reason why we use log here is because we make the assumption that the tree here with the node structure is balanced. So there's the same number of nodes on the left hand side here and the same number of nodes on the right hand side here from our starting parent node. That's why we use log in particular. If the tree was unbalanced, this problem becomes a lot more complicated. But when you do encounter unbalanced trees, they give you a lot more reasoning as to how you go about deriving it. They might say, okay, there's this amount of nodes on the left hand side and there's this amount of nodes on the right hand side, so then you can go about making a mathematical explanation for what's going to be the total amount of nodes accordingly. I remember I started from 0 to 3 here, right? We can say that n here, instead of being 8 for the particular level, we have 15 nodes in total. So that's 1, 2, plus 4, 8. And then we say log 2 of 15 is approximately equal to 4. Because if we incorporate this here, that's actually 4 levels. So either reasoning works. N could be the total number of nodes for the entire tree, or n could be the number of nodes at the lowermost level. Either reasoning is fine once you basically show your reasoning and your deduction regarding this. Right. Further questions? Alright, doesn't look like we have any further questions. Let's go on to our last example. So for our last example here, this code here basically checks to see if a number is going to be prime, but we're only going up to the square root of n. And you may be wondering, okay, where is the square root of n? We see x by x here is less than or equal to n. If our n number here is going to be divisible by some number that's greater than the square root, obviously it's going to be divisible by something smaller than that as a result. So we need to figure out, where do we get the square root of n? And we see here that we have x by x here is less than or equal to n. So let's rewrite this code accordingly to figure out what's going to be our runtime for this. So if we watch inside the loop here, this work is always constant. So we don't really care about this. We're actually going to be analyzing the conditions for a loop here as to figure out what our runtime is going to be. So we know that the loop there started by at x equal 2 and ends when x by x is equal to n. And we can rewrite this such that this here being x squared is equal to n, so x here is equal to the square root of n. So if we rewrite our code here to match that, that means we still obtain the same operation, but we just write it in a nicer fashion for us to analyze it. So instead of having x by x equals to n, we just rewrite this accordingly. So now this just becomes x is less than or equal to the square root of n. So this is the same thing as x is equal to n, just rewritten in another fashion. And because we know that we start at 2 here, and we go up to the square root of n, no matter what value n takes here, the runtime is always going to be O of the square root of n. So we see what's our start point and our end point and how x is changing, and we just put in different values of n to see how it scales accordingly. And once we see that the scaling matches that of O of square root of n, we know that's going to be our order as of such. Right. Any particular questions for example 10 here? The code basically just checks from 2 up to any square root of n here, where n is going to be our input number, to see if it's going to be prime or not to do the divisions. So we like, okay, let's say if this was 5, we'll go x equals to 2 up to the square root of 5, and we just add accordingly, we run that. And if our input number here divided by x returns a remainder of 0, that means we just return false. Otherwise, if it does return a remainder, return true. So for it to be such that we end up getting a remainder for determining a prime number, you just basically go about thinking about it. Okay, let's say if it's 5, typically we'll be like 5 divided by 1. Okay, we just end up with 5. 5 divided by 2 is some decimal. 5 divided by 3, we end up with some decimal. 5 divided by 4, we end up with some decimal. 5 divided by 5, we end up with 1. But there's also another way to go about testing the prime numbers, which instead of going from all those numbers, we just go from 2 up to the square root of that number, and we just keep on doing the divisions to see if we get a remainder or not. So the key points in focusing on these types of questions is that you just basically want to see how the code flow actually operates. So for like iterative questions, you want to see what's going to be the starting point and the end point, as well as how this point for the loop here always so changes. So we know that the starting point here is going to be x equals 2, the end point is going to be square root of n, and x increments by 1. And then we just basically see, okay, how does it scale accordingly in regards to our code here as of such. So a nice way of checking it is to see what's going to be your end condition here for your for loop for the iterative function, and see how you go about scaling it to see if it matches back to O of n, O of square root of n, or n squared, and so forth. For your recursive functions, that means that you're going to have to end up either drawing a recursive tree once you have more than 2 recursive function calls. So like in our Fibonacci series, we had 2 recursive function calls where we had fib n-1 plus fib n-2. Or for our 3 recursive function call we just now said in a previous example, we need to draw those recursive trees in order to see how do we scale it accordingly to match back to our order. And because we see that it scales in powers of 2, that means that we know there's going to be O to 2 to the power of something. And then we can make some logical assumptions regarding these accordingly as of such. So for iterative function calls, you want to analyze how the loop operates. For recursive function calls, you want to see how the recursions operate. And if there are multiple recursion function calls, you're actually going to have to end up drawing a recursion tree to figure out how does it scale to figure out what's going to be. So the complexity is just basically a way of how your code scales regards to your input conditions here. So for example here, if we put in, let's say if we put in a value of 6 here and then I put in a value of 7, 8, 9, 10, we need to see how the time scales accordingly for this code to run. So let's say, in particular, if it goes from 2 up to the square root of some value here, we need to see how many steps it takes in order to figure out, okay, for n equals 3, it takes this amount of steps, n equals 4, it takes this amount of steps, n equals 5, it takes this amount of steps. And then if we graph it, we see that it follows a pattern of order root of n. So that's a nice other way you can go about doing this. But it tends to be a little bit longer when you try doing this, and this only works if you actually have some sort of assistance, be it in the form of a computer or graphical software. You can actually do this scaling for you to observe the pattern. It's a lot more handy if you can actually just analyze the code from these sort of patterns and the sort of tricks that you see here and figure out what's going to end up being the order of the code accordingly. So it's like if we had to test this and we had full assistance, we'd be like, okay, we have a table here, n, and then we have is prime steps, and then we'll end up going from like 2, 3, 4, 5, 6, and then we're gonna get some results here for each one, and then we'll end up doing a graph here where n will be on the x-axis and our y-axis here this will be is prime steps, and we might end up getting some sort of graph either going like this or like this or like something like this. And we just want to figure out what's going to be the nature of that graph. So if it's like some straight line, we know that this is going to be linear, so that's O of n. If it curves something like this, it might be O log of n, and so forth. We just want to know what's going to be the nature of the graph as we scale n accordingly. That's if you're just doing it in regards to some sort of manual scalability. But it helps when you can actually analyze and watch your code and figure out what's this going to be instead of having to plot a graph every single time. So the trick here is just for iterative functions, watch how your loop operates. For recursive functions, you want to watch how the recursion operates And if there's more than one recursion function call, like there's 2 or 3, you actually do want to draw the recursion tree and see how it scales going down in the recursion tree to figure out, okay, the scaling follows this pattern and that pattern matches back to your order. Right, so some advice regarding this. So most of the techniques that you saw in those 10 examples, those are your standard techniques that you're going to end up using to analyze the runtime of the code, of any sort of code. The visualization techniques, such as like the graphing technique I just showed on the previous slide, or your recursive tree technique, it makes it easier to spot these patterns. And once you know the pattern, that's going to be the order of your code. Sometimes, for like example 10, you may have to reorganize your variables mathematically to spot the patterns for the runtime. And the most important thing that you have to pay attention to here is that if there's any sort of ambiguity, do not use a single variable to describe your runtime. Use multiple variables. And this was particularly true when we had the strings in the array being sorted. We did not know what the length of the string was, and we did not know what the length of the array was. And because those two don't have any explicit relationship defined between them, that means they need to be treated as independent variables. And while like a classmate was asking earlier about the assignment 1 and the quiz 1, those are to be released on Wednesday, but you will get full details of that in the forum posts later on tonight. Right. So that basically brings us to the end of our first lecture. Are there any particular questions regarding the material here? You get all those details later. Don't worry about it. You'll get all the details in the forum post. You don't use n here when you have any sort of multiple variables that are not accommodated for in your code. So let's say a good example, the same string arrays that we just now saw. For each string in the array, we don't know if they are the same length. So that's a variable that you need to consider. And we don't know how many strings are in the array, be it in the array size or the array length, which is another variable you need to consider. So when you have multiple things you need to consider, that means that, and there's no explicit relationship between the two of them, being that the length of the string is not exactly going to be the same length of the array, such that the number of strings in the array is not going to be the same number of characters in the string. Those basically are independent variables. So you don't end up using one single variable, you have to use their own variables for each one of these uncertainties. So like another example would be like if you have an array of floating point numbers, but then, and having those floating point numbers, let's say if you have to sort them by length, and then you have to sort them by size, that's going to be a totally different story. Because the length and the size don't actually mean that they are the same thing mathematically. So once you can figure out some established relationship between your uncertainties, you have to treat them as independent variables no matter what. So you don't use n in that particular case. You'd be like, okay, for the length you use L, for the size you use S, and so forth. And you just establish your order in those variables instead. It means that you are unsure if they have any relationship between the two of them. Because, like I said, the length of the string does not mean that it's going to be the length of all the strings in the array. I mean, when I say the length of all the strings in the array, we do not know how many strings are in the array. So the number of strings that are in the array does not mean that is essentially equal to the number of characters for any string. Those have to be treated as independent variables. You just now saw an example of that for your string example. And the explanation that I just now gave a little bit earlier was also another example. Alright, any further questions? No, the response times are basically the same. Because when you do put a comment in the comment sections, it comes in my inbox regardless. So if you email or if you put a comment, it's going to be the same response time. It's not going to make a difference. That's whichever one you prefer. Alright. Doesn't seem like we have anything else in particular, so let's get on to our next lecture. Let's keep my annotations here. Right.